Hello, good afternoon. So, welcome to today's session. Um, and this is going to be the last class for this course. So, today, uh, I hope I'm audible. Yeah. So, today, I mean, in the last class, I had started with some summarizing the portions of this courses, the initial part that involved us going through all the plant structure, leaf structure, where is the photosynthesis occurring in a leaf cell, and what is basically photosynthesis divided into two, it happens in two phases primarily light reaction and the dark, Calvin cycle, and went on until the FPCB model. So today I'll be summarizing. So initially when this course was shared amongst you all, there was this additional topic of C4 leaf physiology added. But instead of that, I had replaced it with working with R and basics of optimization so that it would be helpful for you. I mean, it is a modeling course, so we were looking into the BioPro model, so it would have been helpful for you guys to have a basic knowledge of working with R, so that you on your own can explore the uh, model BioPro. So that's why I did focus more on the C4 photosynthesis and covered almost all of that is important when it comes to modeling photosynthesis in a C3 plant. C3 leaf basically. This course is entirely structured for leaf scale simulations. So after going through the plant structure and FPCB model, what is ACI curves, AQ curves, AT curves, and how the C3 photosynthesis occur, we moved on to the leaf scale water relationship and how this water and the photosynthetic processes are coupled with each other, or we went a little more deeply into how these processes are interlinked with each other. So we talked about stomatal conductance, which is basically the opening and closing of the stomata as by the osmotic potential difference that is happening in guard cells that is surrounding this, I mean, which are main parts of the stomata. And this closing and opening of the stomata is one of the primary uh, physiological process that is allowing for gas exchange to occur. So it is the inlet or it is the entryway for outside gases to get inside the leaf and get inside the plant as well. And the leaf to interaction between the leaf and the atmosphere happens through this stomata basically. And this process where the rate at which this gas exchanging is happening is what we call as stomatal conductance. So in the structure of a leaf, we see that the stomata are present at the lower epidermis, and all these gases are circulating within the spongy mesophyll, and as and when required, is taken by the chloroplasts in the palisade cells. So, stomatal conductance can be defined as the rate of carbon dioxide entering or water vapor exiting through the stomata, and this determined by the degree of opening of the stomata. Basically, the how wide the stomata is open or how narrow it is, and this is offering some physical resistance to the gases traveling through the stomata, and that resistance is again what is called the stomatal resistance, and the reciprocal of the resistance is what we call as stomatal conductance. Now, in general terms, whenever we talk about stomatal conductance, uh, we don't mention that it is stomatal conductance to water vapor or stomatal conductance to carbon dioxide. Instead, we only call it a stomatal conductance. So if any term, if there is any equation or any context where you're talking about stomatal conductance without specifying what gas is being exchanged through the stomata, then by default it is considered that it is the stomatal conductance to water vapor. So stomatal conductance occurs in this stomatal conductance is responsible for photosynthesis because the carbon dioxide that is in the atmosphere enters the leaf through the stomata, and water which is within the leaf exits the leaf through the stomata back into the atmosphere. And this process where CO2 goes in is photosynthesis and water vapor goes out is transpiration. So we see that the stomatal conductance is is influenced by factors by these factors, environmental factors, because here we are talking about the concentration of carbon dioxide within the leaf and outside the leaf, and water vapors vapor pressure, or how much water molecules are present within the leaf and outside the leaf. So one of the major factors that is influencing stomatal conductance is the concentration of these molecules with outside in the atmosphere. So environmental variables or environmental factors are a huge factor that is responsible for this stomatal, or something that is influencing the stomatal conductance. So humidity and carbon dioxide levels. Now light and temperature also plays an important role when it comes to stomatal conductance. Like I said, light maybe not it is not resulting in the opening or closing of the stomata directly, but again it is leading to physiological responses that will change the concentration of water or carbon dioxide within the leaf or outside the leaf, that is going to again result in that is again going to impact the stomatal conductance. Same is with temperature also. Now another factor that influences stomatal conductance are the hormonal signals. Say the plant is being exposed to some kind of stress, then there are certain hormonal signals that will also result in the closure of the stomata. And another important factor is the soil moisture content. The presence of water that is present in the soil is going to affect the water potential in the plant, which is again resulting in a physiological response that will close the stomata under reduced water stress, like drought conditions. The stomata tends to close again for the reason of saving water, so that the plants have sufficient water for the growth purposes, and a lot of water is not lost. Then we looked at the psychrometric chart, how to read a psychrometric chart. A psychrometric chart is giving us the relation of humidity, which is the actual vapor pressure or the actual concentration of water vapor present in the atmosphere at a particular temperature, to the saturated vapor pressure, or the the maximum amount of water vapor that can be available in that atmosphere at that particular temperature. So it is the ratio between the actual and the saturated condition. Generally, it is expressed in terms of grams per kg or grams per gram of dry air, and then it is called the we call that the absolute humidity, the actual condition. Specific humidity is when it is divided by the volume of it. So uh, we um, we went through how to read this chart with a lot of lines crisscross and going here and there. So these curved lines are the ones that represent relative humidity. Relative humidity is represented in terms of uh, percentages. So we have the relative humidity at the curved lines. Then we have these inclined lines that you see are indicative of the saturation temperature or the wet bulb temperature. And that temperature at this 100% line is what is giving you the saturation temperature. Then we have the dry bulb temperature, which is nothing but the normal temperature that we talk whenever we say this is the temperature of the air, then that temperature is called the dry bulb temperature. So wet bulb temperature is nothing but the lowest temperature or the coolest temperature that can be reached when evaporation happens. So during the process of evaporation, some amount of heat is removed from a system, which is going to result in the reduction in temperature from at a small level. So what is the lowest most temperature that is attained as a result of this evaporative cooling is called the wet bulb temperature. Now, how is this different from the saturation temperature is? It is not different from the saturation temperature. Saturation temperature is when the wet bulb temperature is 100%, wet bulb temperature at 100% relative humidity. So this curve, I mean the temperature that is corresponding uh, or coinciding with this 100% relative humidity curve is the saturation temperature, which is nothing but the wet bulb temperature at relative humidity 100%. Now there is something else called the dew point temperature that also which you will come across in psychrometric data or data that is related to relative humidity. And this dew point temperature is the temperature, again, the wet bulb temperature if it is representing the lowest temperature, then at that particular temperature itself, when say more, when the heat is removed more, the condensation process occurs. And the temperature at which the condensation begins, that is when the relative humidity is 100%, when the air is fully saturated, then the temperature at which this condensation begins is called the dew point temperature. And how is it different from the saturation temperatures? At saturation temperature, no condensation is occurring. I had in later classes talked about the latent heat and the sensible heat concept. So latent heat is when there is a phase change, and sensible heat is when the temperature is changing. So in saturation temperature, the phase change is not occurring. Evaporation occurs, but as a result of which the temperature reduces, but no condensation occurs. Now, at that particular temperature, when more heat is removed from the system, condensation occurs, but there will not be any temperature change. So the temperature when the air is fully saturated with water vapor and the condensation starts, when the condensation begins, is called the dew point temperature. And we also did a couple of problems how to extract the data from the psychrometric chart and use it in some of the equations that we require to. Yeah. Then we moved on. So we covered the concept of stomatal conductance. We covered the concept of humidity, which is an environmental factor that the stomatal conductance depends on. And we then move on to this transpiration process, which is nothing but the removal of water from the leaf. Now, water from transpiration is an important process because it is helping the plant to maintain temperature, and it is bringing about this cooling effect on plant, that is removing some heat from the plant when the water is evaporated from the leaf, or water exits the leaf through the stomata in the form of paper. Um, so the driving force for this transpiration process is the vapor pressure deficit. So transpiration, stomatal conductance, and humidity are related in this form, where the transpiration is a product of the stomatal conductance, the rate at which the stomata is opening, and the vapor pressure deficit. Now, vapor pressure deficit is nothing but it is the difference in the vapor, that is the vapor pressure within the leaf and outside the leaf. So within the leaf, say if we are expressing the concentration of water vapor in terms of vapor pressure or molecules of water vapor, irrespective of that, what is the difference in the quantity of water or amount of water or pressure of water within the leaf, and what is the difference between what is in the outside atmosphere, that is outside the leaf, is called the vapor pressure deficit when it comes to plant physiology or representation of this transpiration process. So this difference in the concentration or amount or vapor pressure is called as vapor pressure deficit. Why I'm stressing on amount or concentration or mole fraction or vapor pressure is because In the hydrology, vapor pressure deficit is defined as the difference in the vapor pressure between two points. But in plant biology, if we don't represent vapor pressure deficit only in terms of vapor pressure, we also call the difference in the mole fraction of water within the leaf and outside the leaf as vapor pressure deficit. So there is it's not contradictory, but it is a little bit problematic when we use this term vapor pressure deficit in plant and represent vapor pressure not as the pressure value but as a mole fraction. When we make estimations, there is a bit of confusion with the units and all, because when we say vapor pressure deficit, it means it is a difference in the vapor pressure. But as we have seen in the previous classes in estimations, we are representing the concentration of water vapor within the leaf in terms of mole fraction and not vapor pressure. So that is why even though we use the term vapor pressure deficit, it actually means the concentration of water vapor inside and outside. So here, let us continue using VPD as a term for ease of explanation. So VPD reducing means the within the leaf, the vapor pressure or the concentration of water vapor is always considered as in a saturated state. So it is only then. No, this we are talking about the C3 photosynthesis. I'm not talking about different species plants. I mean, there are plants with having stomata on top as well as bottom. This is not going in species specific or plant specific or anything. C3 photosynthesis, when we represent in terms of modeling, this is what is stomatal conductance. So,
Okay.
when the vapor pressure or the concentration of water vapor within the leaf is always saturated, and outside it is going to be lower than what is inside the leaf. And outside, when the vapor pressure reduces, it results in an increase in the vapor pressure deficit. And this vapor pressure increase is going to result in higher temperature, because the relation between vapor pressure deficit and transpiration is directly proportional to it. So at high RH, that is when the actual vapor pressure, the outside vapor pressure is low, there is a tendency for the vapor pressure deficit to increase, which will result in the increase of transpiration. Now, as a consequence to it, what happens is the stomatal conductance to water vapor will reduce, so that more water is not lost out because of this vapor pressure deficit. So this is how transpiration, stomatal conductance, and relative humidity is linked. Now, the same connection is there for the gas exchange happening in terms of carbon dioxide also. So photosynthesis is happening when there is a change. It is not happening because of the change in the concentration of carbon dioxide, but that is also a driving force. So when the carbon dioxide concentration outside is more than what is inside, then carbon dioxide is going to enter the leaf through the stomata. Again, this is also linked, the stomatal conductance, product of stomatal conductance, and this difference is what gives us the value of assimilation. Now we see there are three or four, five quantities that are interlinked with each other. A is linked to stomatal conductance. Stomatal conductance is linked to the concentration of water vapor. Stomatal conductance is linked to the concentration of carbon dioxide. The concentration of water vapor is linked to transpiration. So when we have to establish a relation between assimilation and transpiration, there are like four factors that are going to play a role in it. So it is a highly non-linear system. When one increases, one decreases. So when that decreases, this decreases or increases. So it's a very non-linear system. Yeah, so high VPD means the actual vapor pressure is low, which is resulting in low, which means it is low relative humidity. So the transpiration rate will become high, which is going to result in the stomatal conductance to reduce to save water loss. But when it comes to the vapor pressure deficit being low, and which means that it is high relative humidity outside, the transpiration rate is going to be low. So stomatal conductance is not going to it is not going to be affected by the transpiration rate or vapor pressure deficit. And if there is any change, it might be probably because of the photosynthetic process. We also looked at how we can connect the stomatal conductance of water vapor and the carbon dioxide. Now, the values of stomatal conductance, that is the rate at which carbon dioxide enters the leaf and the rate at which water leaves the leaf are different. Now, for the same condition, both the rates are going to be different. So the stomata has to come to such a opening size so that it will allow sufficient carbon dioxide inside and it will control sufficient water outside the system. Now the values of GSW, which is stomatal conductance to water, and stomatal conductance to carbon dioxide, is linked by this diffusivity coefficient, which is 1.6 in terms of diffusivity of water to carbon dioxide, and it is obtained using this Graham's law, where the diffusion is inversely proportional to the square root of the molar mass of carbon dioxide and water. And so we get the diffusivity coefficient as 1.6. So in that case, GSC, which is the the stomatal conductance of water, is 1.6 times larger than the stomatal conductance to carbon dioxide. So that means that water travels at a speed or a rate faster than carbon dioxide, obviously because of the difference in the molecular sizes. One is 18, another one has a molar mass of 18 and another has a molar mass of 44. So carbon dioxide tends to travel slowly, but water in the same time will travel faster. So if you have a stomatal conductance of 10 for water, then the amount of carbon dioxide is 1.6 times lesser than water, and only that much amount of carbon dioxide will leave the system. So this was one important uh, connection that we had looked into. And we also looked at how we are getting the unit of stomatal conductance. So stomatal conductance, whenever the unit of is stomatal conductance is always represented in moles per meter square per second. And VPD, since it is associated with water, in millimoles, and transpiration also in millimoles per meter square per second. And assimilation will be in micromoles per meter square per second, and the concentration will be in micromoles per moles of air. So particularly in terms of modeling, not only in modeling, even when it comes to measurements in Likert, the whenever we look at the units, we have to keep in mind that stomatal conductance is best represented as moles per meter square per second. It is only then we can represent these values in its actual values of millimoles, micromoles, etc. Then we also looked at a way where we can convert the absolute humidity or the actual vapor pressure when given in grams per kilogram to mole fraction. It is you have to divide whatever value you get by the molar mass, and then divided by the sum of the molar mass of water, moles of water to moles in air. And we looked into some interesting problems in order to familiarize with these concepts. So we talked a lot about how all these terms are very much linked with each other. Transpiration is linked to stomatal conductance of water vapor, and that is also dependent on the vapor pressure deficit. Now, this stomatal conductance is also dependent on the stomatal conductance to carbon dioxide, which is again dependent on the carbon dioxide concentration, again effective assimilation rate. So, in order to make this concept, this nonlinear concept, into a simpler concept, these scientists developed this Ballberry model, which is establishing a direct relationship. Now, what we saw is a very indirect nonlinear relationship. So they developed this direct relationship between uh, direct relationship between stomatal conductance, photosynthetic rate, vapor pressure, that is humidity, and carbon dioxide concentration. So this in this model, the relative humidity that is considered is the relative humidity at the surface of the leaf and carbon dioxide concentration at the surface of the leaf. And this relation was obtained between the stomatal conductance and photosynthetic rate, which is a linear relationship given by the parameters B naught and B1. Sorry, just a second. This is B1 and this is B naught. Okay. So there is a linear model that has developed a linear relationship between stomatal conductance and photosynthetic rate, as well as the environmental variables, and the slope parameter, which is giving the relation, the slope of the curve. Linear regression. We do a linear regression model. We run a linear regression model to whatever data we have, and we find a linear curve, linear line, the slope of the line, and the intercept of the line. The slope of the line, slope of the line is what is giving us the sensitivity of the stomatal conductance to changing photosynthetic rate, and the intercept of the line is giving us the baseline conductance, that is what stomatal conductance will occur even when there is no photosynthesis is occurring. So in order to understand this relation, we consider, say, for the sake of understanding, suppose the relative humidity, ratio of relative humidity to carbon dioxide concentration is 1, then only changing factor here is the the assimilation rate. So when the assimilation rate changes, GSW also keeps on increasing. Uh, and in these two curves, if you see, the one with a higher slope, there is a higher level of increase, but one with a lower slope, there's a lower level of increase, a lower rate of increase. So you see, if this value between 5 and 10, stomata is changing from say 0.3 to maybe 0.3 to maybe 0.6. But when you consider this planned one, for the same change in photosynthesis from 5 to 10, the stomatal conductance is varying from 0.6 to 1.1, which is a huge level of change. So that is why we say that stomatal, the slope parameter is giving us how sensitive the stomatal conductance is to photosynthetic rate. And the intercept is again giving us a baseline conductance, that is this value when An is equal to 0. Now, ideally, the humidity is not going to be 0, neither is the carbon dioxide concentration going to be 0. So if An can be 0, it can, I mean, no photosynthesis can occur in a leaf during night time when there is no light. So under such condition, stomata is not going to still completely close. It is going to be open at a very low level, and that level is represented by this interceptor. Now, when this model was developed, it was assumed that there is no water stress. That is, there is no uh, limitation to water available for the plant. The plant has got plenty of amount of water, and so the only limiting factors are the uh, humidity in the air and the carbon dioxide concentration in the air, and the time of the day. That is whether photosynthesis will be 0 or it will have a value. And since this Baldberry model is only considering or talking about the environmental variables effect and how the photosynthesis is varying with stomatal conductance, we have to additionally also consider the soil water stress. That is a situation where a situation where there is water stress experienced by the leaf, and what will happen to the stomata under such conditions. So in order to do that, we have this soil water, we have a stomata water stress function, that is represented as a fact, represented in terms of the relation with soil water content or soil water potential. So when depending on what is the percentage of soil or the soil volumetric water content in the soil, I had explained what volumetric water content is. It is the volume of water present in the soil to the total volume of the soil. And depending on what is the water content, which is something that we can measure using a lot of instruments, a lot of technology. And also by understanding what is the field capacity of the particular soil and the wilting point of the particular soil, we can find out the stomata water stress function, which we have to apply on our calculations of transpiration and assembly, particularly transpiration and stomatal conductance, because stomatal conductance is also affected by uh, the soil water content. So depending on how much water is how much water is present in the soil, whether is it equal to the field capacity or whether it is less than the wilting point, the stomata is going to close. It is going to send some signals to the, I mean, the water potential is going to reduce, and this reduction in water potential is going to reduce the osmotic potential in the guard cells, which is going to then lose water, resulting in the closure of the stomata. So, yeah, and this Ballberry model, we also went through how this linear regression function is developed. Say we have the data of stomatal conductance and the data of all these data, AN, HS, and CS. And if you want to find it out, then a linear regression model is done this way by finding the mean and the and the product of the value, the differences of the mean, making use of this formula, and how we find the intercept value, which will help in getting the Ballberry parameters. So the Ballberry model and the relation of stomata water stress that is giving us a stomatal water stress factor is taking care of how the stomatal conductance is influenced. I mean, giving us a look into how stomatal conductance is okay. How stomatal conductance is influenced by the atmospheric parameters and how it is influenced by the below ground parameters. Now, whenever we are looking at this Ballberry model is taking into consideration the relative humidity at the surface of the leaf and the carbon dioxide concentration on the surface of the leaf. We are not talking about a general relative humidity value that we have looked at, got obtained from the psychrometric chart. And why that is specifically told as the surface conditions, relative humidity and carbon dioxide concentration, is because apart from stomatal conductance, whenever the carbon dioxide has to go reach till inside the leaf, they also have to go through this boundary layer. That is a layer of air that is going to offer some resistance to the passage of carbon dioxide and water vapor, etc. So it has to cross this boundary layer also, and this boundary layer is going to offer some resistance to it. So the total conductance or total resistance to carbon dioxide and water vapor is always a combination of the resistance offered by the boundary layer and the resistance offered by the stomata for the passage of carbon dioxide at every level. Now, atmospheric carbon dioxide first has to go through this resistance that is offered by the boundary layer and reach the surface of the leaf. Now, from the surface of the leaf, when it is going inside the leaf, again it is affected by the stomatal resistance. Now, resistance is conductance is the reciprocal of resistance, so we can get the values of appropriately by using it. So, if the resistance term, the sum of the resistance is what is the total resistance, then you have to substitute the reciprocal of these values to get the total conductance. So the boundary layer conductance This will be the boundary layer conductance to carbon dioxide in the atmosphere to carbon dioxide on the surface of the leaf. Then carbon dioxide on the surface of the leaf will undergo a resistance by the stomata to enter the stomata inside the leaf. Same is the condition with water vapor also. Water vapor also, water has to first face this resistance by the boundary layer, and then it has to reach the surface. Now, in case of water vapor, it is going out. So because of that, the water vapor which is going out, first it is having to face the resistance from the stomata, and then once it has to reach this level of where we can actually estimate from the psychrometric chart what is the actual vapor pressure, then it has to go through this boundary layer also. So like I said, the sum of the resistances will give you total resistance is the sum of boundary layer resistance and stomatal resistance. But when you consider, because it is it is connected in a series way, but the same thing when you convert it to the conductance, it becomes a reciprocal of it. So the total conductance will be 1 by G1 plus 1 by G2. So leaf is following this system where there is a series connection between the conductance or resistance. Now, if we get the total conductance to water vapor as by using it in this formula, so we see the total conductance is equal to 1 by G1 plus 1 by G2. If G1 is the boundary layer conductance and G2 is the stomatal conductance, then we get the total conductance in this way. GSW and GBW by GSW plus GBW. Now, suppose you want to find it out for the total conductance of carbon dioxide, we have to apply the diffusivity coefficient on the stomatal conductance. But when we apply the diffusivity coefficient in the boundary layer conductance, we see that the value is varying to 1.37. And that is because when it comes to boundary layer, it is not just the molecular weight that is going to be a factor in estimating the diffusion. The eddy diffusion, turbulence, all of that also plays a role in it. So that is why the value changes accordingly. There is a law that helps us in finding the diffusivity coefficient when boundary layer is in play. So in the end, the instrument that we had looked into, the Leica instrument and the model BioCro, all of them estimate this CI value from these equations. That is, if you see, the assimilation rate is equal to stomatal conductance to and the difference of the leaf surface carbon dioxide concentration and the concentration of intercellular carbon dioxide concentration. So CI will be equal to CA CA minus A by GTC, and if we have to obtain the CI value with the carbon dioxide concentration on the surface, then it will CI will be equal to C surface minus A by GSC. Here again, wait, C surface is equal to A by GSC plus CI. This is plus. So it is from this relation that models are figuring out how to find, because we have the Ballberry model in BioPro. How is the Ballberry model estimating the surface carbon dioxide concentration is from this equation. They are able to measure the carbon dioxide concentration within the chamber, and that is the reference chamber and the sample chamber. So they have the value of CA, and they have the value outside the chamber. So what they do is estimate the GSC. Again, you can get it from the Leica instrument. We have the measured A value also, and from that they will obtain this C surface value, which in turn we can use in the Ballberry model. So this is just a look into what is obtained from what is again different when you're using an instrument for measuring and different when you are modeling. When you're using an instrument for measuring, we are actually getting the actual values. And if we use these actual values, we are able to obtain some values of intercellular carbon dioxide or carbon dioxide on the surface, etc. Now, these values can be used in a plant model. in order to obtain other values which we don't have access to. So this is how planned modeling or experimenting and modeling approaches uh, work with finding the quantities. Sorry. Okay, I'll take a 2 minute break and then we'll move on to this leaf energy balance model. Okay. So the next, till now we were dealing with photosynthesis, we were dealing with stomatal conductance, we were dealing with transpiration. A huge shift from all of that. Those are all very interlinked processes. This is also linked to that, but a huge shift is this energy balance module, which is looking into this temperature and how is the plant or the leaf balancing the total, all kinds of energy that it is receiving. So basically, energy is neither created nor destroyed. So whatever energy the plant receives is either released out completely, or if it is not completely released, then some part of it is stored in the system. And in terms of a plant, whatever the energy that is received by the plant is mainly the radiation. That is solar radiation and long wave radiation. Solar radiation is nothing but all the rays from the sun, and long wave radiation is again but the heat that is that is available to the plants from the surrounding. That is, there is heat generated by the soil, heat generated by the earth, atmosphere, and some particles in the atmosphere is all are generating heat, and that available heat, or the heat that is absorbed by the plant, is what is long wave radiations from surroundings. And the outgoing energy components are radiative heat loss. Again, the heat that is generated by the plant is let out. Then there is sensible heat loss and latent heat loss. And apart from that, like some of the amount of heat that is taken in by the plants have to be utilized. So a large chunk of energy is utilized in the manufacture of carbohydrates, which is during the photosynthesis, and also for various temperature regulatory process, and various other functions that is used in a plant. And I am totally not aware about what are those processes, which requires going deeply into all of the processes that is happening in a plant. So we are only looking at the superficial estimation of energy balance. That is how, what is coming out, what is going in, and what is being stored. So if we know what is going inside, and if we know what is going outside, we will be able to obtain what is actually being stored in the plant. But we don't know how that stored energy is utilized by the plant. It is utilized again for various purposes by the plant. But we just know the total energy that is available to the plant, what is released by the plant, so what will be stored by the plant. Now, in terms of radiation, again, the shortwave radiation is nothing but the radiation by sun's light that is coming in the spectrum of ultraviolet rays to near infrared rays. So, ultraviolet rays start from 10 nanometers, but plants, what the solar radiation that can be used as an input to the plant lies in the range of 100 nanometers, and then all along the visible light until the near infrared light, which goes to about 3000 nanometers, not the full infrared spectrum, only the near infrared spectrum. So if you're looking at studies related to plant, the most important parts of the electromagnetic spectrum to be considered is the ones that is ranging from 100 nanometers of ultraviolet rays till 3000 nanometers of infrared rays. And all of these rays are utilized, but again, when it comes to chlorophyll fluorescence and various the photosynthetic study, we are familiar with the visible light spectrum that is available or utilized by the plants, which is between the 380 nanometers to around 780 nanometers of and the blue light and the red light is what is very much important to the spectrum. The wavelengths of this wavelengths in the visible light is what is very much important to the plants. We also talked about the Leica instrument, which is an infrared gas exchange analyzer, which is making use of this infrared light, belonging to some spectrum of the infrared range, to measure the concentration of carbon dioxide and water vapor. And when it comes to long wave radiation, again, long wave radiation is refers to this portion where the heat is generated, mostly the ones with a higher wavelength. So the speciality of lower wavelength lights is that they are high energy, and the larger wavelength or higher wavelength, lower wavelength is high energy, higher wavelength is low energy. And this spectrum of 0.004 to 0.03 mm, that is the far infrared spectrum, is what is majorly contributing to the long wave radiations that is available to the plants. So if you see, whether it is the absorbed radiation, long wave radiation, or emitted radiation, it will somehow fall into the far infrared wavelength. So that is the difference between short wavelength and short wave radiation and uh, long wave radiation. Again, short wave radiation is in the form of direct or diffuse light. That is, direct light is direct rays of the sunlight. Diffuse light is probably this light is being obstructed by, say, something, and then it is this diffused wavelengths are also being absorbed by the plant. Long wavelengths are the thermal heat, that is the heat energy. Infrared radiation again is referred to as thermal radiation. This thermal radiation that is reflected by the Earth's surface, by the atmosphere, by the clouds. All those thermal radiation having energy in the spectrum of far infrared rays is what is available to the plants. Now, if you see, like I said, again, there is a threshold of wavelengths within which are the energy that can be utilized by the plants. It is not making use of all the energy that is available. It is making use of this particular energy within a particular range of electromagnetic wavelength. Now, in within this short wave radiation and long wave radiation the plant gets. Now, suppose we have a chunk of short wave radiation going on to the plant is not going to absorb all of it. It will only absorb around 50 to 80% of whatever it receives. So whenever we have data like the humidity data itself, we will only know what amount of light the sun is releasing. We have instruments to measure it, but we shouldn't be assuming that all of that light is taken up by the plant. So we have to consider only 45-50. Generally, in estimations, 45-50% of it is considered, but if you consider a wide range of plants, around 50 to 80% is only taken up by the plants. So this amount of light that is photosynthetically useful to the plant is called the plant available radiation, and that is what you will see in a lot of data that is simulated by crop models. You don't get whenever you have the radiation data that is simulated by crop models, the data will not be available as radiation alone, but plant available radiation. And it is up to us, or it is up to us to add a line in the code, or up to us to use that data and convert it to the actual solar radiation in order to, estimate how much, what is the impact of solar radiation, say, on a process. Then we have to understand the difference between what is available to the plant and what is the actual radiation that is coming from the sun. Now, again, if you see in plant available radiation, they are expressed in units of micromoles of photons per meter square per second. And this is because we are converting it into the photon flux density, which is often called as the photosynthetic photon flux density. Now, photosynthetic photon flux density is nothing but how many light particles, that is photons, are hitting the surface of the leaf, hitting a meter square of the surface, a unit area of the leaf in a unit time. So, specifically, the meter square of the leaf in 1 second's time, how many light particles are being absorbed by the plant, or how many light particles are available to the plant, is what is called PPFD. Photon, a tiny particle of light. Flux is the number of photons that are moving per unit area or in a certain area. And density is the total concentration of the photons in that area. Now, by the Avogadro's number, we know that 1 micromole of photon is equal to 6.022 into 10 to the power 17 photons. That is, if you consider 1 mole of photons, just like how you consider molar mass, there's 18 grams per mole of water, there is 44 grams per mole of carbon dioxide. Per mole of photons means it consists of 6.022 into 10 to the power 23 photons, which is called the which is called the Avogadro's number. And this photon flux density is not a measure of anything else in the infrared or the ultraviolet spectrum. It is only the measure of data that is falling between the ranges of 400 to 700 nanometer range. So in order to convert whatever solar radiation we have to this final PPFD, we have to first consider how much percentage is available to the plant. Then we have to use this E is equal to Hc by lambda, the that is energy, linking the energy with the wavelengths, the equation, Planck's equation, to find out what is the energy of one photon. So if we know the energy of one photon, we have 6.022 into 10 to the power 23 photons available. What is going to be the energy of this many number of photons we can estimate. And for that, if we have the Planck's constant, which is again a constant value, velocity also we know. And if we have the wavelength of that particular light that we are taking into consideration, then we can find the energy of one photon. And that energy, if you multiply it by the Avogadro's number, you will get the energy of a mole of photons. So 1 mole of photon is equal to the number of photons into the energy of one photon. And finally, you will get a value like this. Say this lambda value is always varying. We talked about it in a range, 400 to 700 nanometers. So since it is within a range, we cannot impose one particular value, but all the other values are constants. So we finally get that the energy of a mole of photon is equal to 0.1198 by lambda joules per mole. Now, since we know that this equation, the PP solar, in order to know what is the photon flux density, we take in what is the solar radiation that is available to us and divided by the energy of 1 mole of photons, and we will get the photon flux density. So, by using this final equation, you can find out, and if you have access to the data wavelength, that is which wavelength of light is, particularly it is mostly the blue and the red light is what is of major focus when it comes to chlorophyll fluorescence studies. So if we know what wavelength is required by us, then we can substitute in this and find out the solar radiation, the plant available radiation in terms of PPFT. To be careful that lambda value has to be substituted in terms of meter. Now, if you don't want to remember what unit in it, this is how you will generally find out the convert the solar radiation to PPFT. So we talked about how this solar radiation, which is the shortwave radiation, can be interpreted in terms of the weather data to what is available to the plants. Now, long wave radiation is also being taken in the plants released by the plants, and there are studies that say that, and most of the studies say that if there's only 40 to 80% of shortwave radiation that is taken up by the plants, around 96% of the long wave radiation that is incident on leaf is taken up by it and also released by it. So why is this high range existing in terms of long wave radiations? Because leaves behave like black bodies in the long wave infrared region. So uh, they emit as well as absorb the same amount of thermal radiation. So if there is some amount of thermal radiation available to us, 96% of it is also absorbed. It will also release 96% of equivalent amounts of thermal radiation. And this radiative heat loss. Now, we are not generally, when it comes to estimations, I don't exactly know why that long wave radiations are not considered as an input. In this diagram, it is considered as an input, but in the long wave radiations equation the leaf energy balance equation, we always consider it as the energy that is released rather than energy that is absorbed. So if we have some amount of long wave radiation, it is always assumed to be the energy that is or the thermal radiation that is released. And how to estimate this radiative heat loss or long wave radiation heat losses using this Stephen Boltzmann's equation, emissivity factor into the Stephen Boltzmann's constant, and the leaf temperature raised to the power 4. The leaf temperature. This is the equation of the black body. And here emissivity factor is taken as around to lie in between 0.8 and 0.98. And temperature is expressed in units of Kelvin. Stephen Boltzmann constant we know is this value. It is a constant value. Okay. So we looked at what are the radiations available as input, long wave as well as short wave radiation. So in this picture, you can clearly see there is some direct radiation available to plants, diffuse short wave radiation available to plants, long wave input is available to plants. Now reflected short wave radiation is also available to plants. So short wave radiations can be available in form of the direct light, diffuse light, and reflected light. A long wave radiation from whatever the surroundings and all is also available as input. Now, if we consider the energy that is going out, it is also releasing the short wave. It cannot emit short wave radiation, obviously. So short wave radiation, some of it which are reaching the leaf surface will be reflected out. So some estimations take into consider that again, depending on the requirement. But the major forms of energy that is released is the thermal radiation from the plant. The plant is going to emit heat. Then there is sensible heat loss and then latent heat loss. So thermal radiation by the plant is given by this equation, Stephen Boltzmann's constant. The sensible heat loss, like I talked about in the when we were talking about the wet bulb temperature, saturation temperature, and dew point temperature, when an object is heated, its temperature will rise. As long as you keep adding heat to an object, it will keep on rising. This change in the temperature of an object as heat is kept on adding, or as heat energy is kept on adding, is what is called the sensible heat loss. So when heat is removed from an object and the temperature falls, then this heat removed in plants particularly is called the sensible heat loss. Now in plants, um, when the plants remove heat, the temperature loss is going to happen. And this removal of heat happens in two ways, either through conduction and through the convection process. The conduction process is occurring when there's direct contact of this leaf with the air. So if you see here, just like how there was resistance offered to the movement of carbon dioxide and water inside and outside, heat is also having some resistance offered to it. So when heat is leaving the system, it is having to face resistance by the boundary layer. Now around the leaf, this boundary layer is like a layer of air that is stuck around the leaf. So when the heat is moving from the leaf to the outside, when the heat released by the leaf is going outside, it has to face the resistance because of this boundary layer. So this direct transfer of heat through this leaf being in touch with the boundary layer is what is called the sensible heat loss through conduction. So heat is actually being transferred from the leaf into the boundary layer, and you can actually consider this boundary layer as another surface and the leaf as another surface. So when the leaf is in contact with the boundary layer, heat is being transferred from the leaf to the boundary layer, which is the sensible heat loss through conduction or sensible heat loss through direct contact. Now the other process in which heat will leaf or sensible heat is lost by the plant is through convection. Now, whatever heat is being transferred from the leaf to the boundary layer, it is going to stay in the boundary layer itself, or it is going to be removed by the wind that is blowing over the leaf. So when the wind blows over the leaf, the wind is going to carry away some heat that is there in the boundary layer. Now, suppose there is no wind, means this heat will slowly, it is warm, the boundary layer is warm. So we know that warm air rises and cool air settles. So this warm air will slowly rise from the boundary layer, or if there is wind, it will result in removing this heat from the boundary layer. So the sensible heat loss through a leaf is a combination of the sensible heat loss due to conduction and sensible heat loss through the convection process. So wind is going to, the leaf warms the air above. This is sensible heat loss due to conduction. This heat transfer to the boundary layer is carried away by wind. If the wind is lighter, then wind is not going to carry away. Instead, the heat, the warm air itself rises on its own. It is called natural convection. And if the wind is blowing it away, then it is called forced convection. So sensible heat loss through conduction and convection uh, is one form in which leaves lose out their heat energy. First one is the thermal radiation by the leaf. And the key factors that is affecting the convective heat loss is again how broad the leaf is. Now, if the leaf is very broad, it will also have a higher boundary layer, I mean more boundary layer around it. So the convective heat loss will be, I think it will take more effort for the wind to remove the hair. Now, again, if the leaf is narrow, again it is easier for it to lose heat because the boundary layer will be less on or smaller around it. Now, if the leaf surface has got these hairy structures called trichomes and all, then again it is more difficult for the wind to remove the air. So, the rate of convective heat transfer, that is convective sensible heat transfer, is directly proportional to the square root of the speed of the wind, and ratio of the speed of the wind and the leaf width. So whenever we look into the heat leaf energy balance involving sensible heat loss, one important parameter that we'll have to take into consideration is temperature of the leaf and also the wind speed that is existing outside. So it is only if we know the wind speed that we can estimate what is the convective heat loss, convective sensible heat loss. So the sensible heat loss can be summed up into this one equation as the product of the specific heat capacity of air into the density of air multiplied by the difference in the leaf temperature and the air temperature and divided by the resistance offered by the boundary layer. So this leaf temperature is taking care of the sensible heat loss through uh, this is yeah, this is leaf temperature difference is there because here the temperature is changing. Heat is as the heat leaves, the temperature also changes, and this RH is taking care of the convective heat loss because if only if we know the resistance offered by the boundary layer can we take into account the convective heat loss. And boundary layer is also important in estimating how much of conduction is happening. So if there's a huge boundary layer, again, the conduction will be more. Conduction will be less. Sorry. Resistance will be more, conduction will be less. Now, the third kind of heat loss is latent heat loss. So till now, we looked at how when energy is lost, there's a temperature difference. But sometimes when the heat energy is removed from a system, there will not be any change in temperature. So at 100 degrees Celsius, water will be at liquid also, and 100 degrees Celsius, water will also be at the vapor phase. And this is called the latent heat of vaporization. So for ice to liquefy from the solid state to the liquid state, there is no change in temperature occurring. At 0 degree Celsius itself, you will see that it is still ice. And at 0 degree Celsius itself, you will see that it is slowly changing its phase from solid to liquid. This transfer in phase is what is called as the latent heat of vaporization. So this latent heat of loss of water is based on this principle of latent heat of vaporization. So in case of plants, whatever is inside the water which is in the liquid phase is going to get transferred into water vapor during this major process called transpiration. During that transpiration, cooling is happening, but there is no temperature change happening. Only heat is lost. There is no temperature difference in this during this kind of heat loss. And latent heat, we can estimate latent heat through the Penman-Monteith equation. There are a lot of other equations. I took out this Penman-Monteith equation because this is what is commonly used. Again, Penman-Monteith equation is the latent heat of vaporization is a function of the air temperature. And this Penman-Monteith equation, if you see, again, is a function of the slope of saturation vapor pressure curve. Slope of saturation vapor pressure curve is nothing but this line you see here, this 100% relative humidity line. The graph with that 100% humidity and temperature is called the saturation vapor pressure versus uh, temperature graph. So the slope of that line, whatever slope value you're getting is what is delta here. 5N is the net radiation. Net radiation is again net whatever input radiation is there, that is short wave, direct radiation, diffuse radiation, reflected radiation, all input and all output, and the long wave input and long wave output. So net radiation is the short wave input, short wave output, short wave input minus short wave output, and long wave input minus long wave output. Then the saturation vapor pressure inside the leaf, the saturation vapor pressure outside the leaf, density, again specific heat capacity of air, the stomatal conductance, the aerodynamic conductance, again which is a factor of the boundary layer conductance. This equation again can be modified to fit that for a plant, exclusively for a plant, by considering this Ga as the boundary layer conductance. And all of these are functions of you can see this is psychrometric constant is relation between the wavelength and the specific heat capacity of air in the density. So you can substitute these terms with the specific psychrometric constant, and then you can see that the equation can be further simplified into this form you see here, where we are using psychrometric constant instead of all this rho and CPM. And the latent heat of vaporization. Lambda is the latent heat of vaporization, not the wavelength. Sorry. So this is how a latent heat loss can be estimated. So finally, we can estimate the leaf energy budget as the input values of short wave and the long wave radiation, output values of the short wave and the long wave radiation, plus the sensible heat loss, plus the latent heat loss, and the G value is talking about the stored energy. So this is the leaf energy budget equation, which is summing up the energy inside, energy outside, and the energy that is stored. Now, this equation itself, it is simplified into this equation that I'm pointing my pointer into here. Rn is equal to H plus Le plus G, where Rn will be the net radiation. That is the total incoming short wave and long wave radiation minus the short wave and long wave radiation that is going out. So that is what is called as a net radiation. Now, this net radiation, this long wave radiation can also be represented in terms of this temperature of the leaf, and the sensible heat is represented in terms of this equation. So the final equation is again going to be the total light intensity, light that is available to the plant minus the thermal radiation that is emitted by the plant, sensible heat loss, latent heat loss, and stored energy. So this is also a very important thing that has to be put into a crop model, because again the process of transpiration and photosynthesis is linked to this temperature of the leaf, where you can see this part will take care of the temperature of the photosynthesis process. This part is taking care of the stomatal conductance and transpiration. So all of these processes are interlinked, and hence this is a very important representation in terms of plant volume. Now, another important thing that we looked into in leaf energy balance is the temperature response function. So I had taken this temperature response function where we are linking all of these terms that are involved in the biochemical processes like Bc max, J max, PPU rate. All of these are linked to the temperature. So what function is giving us this connection of these parameters, and the temperature is what is given by these temperature response equations or temperature response functions. And one such equation is the Arrhenius equation. So Arrhenius was is an equation that was proposed by Svante Arrhenius on the work of another chemist. And this is giving us a dependence of this enzymatic reaction. Now, the enzymatic reaction, which we know in plant physiology, is the reaction of RuBP with carbon dioxide catalyzed by the Rubisco enzyme. So this enzymatic reaction is linked to the temperature using this Arrhenius equation. This is the Arrhenius equation, which is giving us this rate constant K as a product of the frequency factor and the exponential factor of activation energy R and T, which is a factor of the again temperature and the ideal gas constant. Now, often this, if you see, when the temperature approaches infinity, this term minus EA by RT will be equal to 0. So e to the power 0 is equal to 1. So then the rate constant can be defined as the frequency factor, or A can be defined as the rate constant when the temperature reaches infinity. Now, temperature reaching infinity is not a possibility. So that is why this A value is not given much importance. And instead of A, what we do is we define a reference temperature, and then we modify the equation by finding out the rate constant corresponding to that reference temperature, and then substituting this equation for A. That is, K naught is the rate constant at a reference temperature T, and K naught, this value will be substituted in this Arrhenius equation, and finally the Arrhenius equation is written as K naught into e to the power C minus EA by RT, where C is the dimensionless parameter, EA is the activation energy, R is the ideal gas constant, T the temperature in Kelvin, K naught is the rate constant corresponding to the reference temperature. So it is in, if you observe this format of the equation and see how it is used in our photosynthesis model, is this constant Kc, which is Michaelis-Menten constant for carbon dioxide and oxygen. You can see it is represented in this way: e to the power 38.05 minus 79.43 by R into Tn. Now this 38.05 is the C constant, that is this value that you see here, C value. 79.43 is the EA value. R and TL we know. And if you see, K naught is nothing over here. So K naught is equal to 1. And it is said that K naught for Kc, that is Kc at a temperature of 25 degrees Celsius is considered as 1. So that is the reference temperature that is taken into consideration here. Same in the case of K naught also. Only thing, the value of C and activation energy changes because it is considering oxygen over here. Gamma star is also given by this, is related to the temperature in this using this Arrhenius equation. And here, if you see, we have the maximum rate of Rubisco carboxylation given by this Arrhenius equation. Here we see that Vc max is not equal to 1. So we have to, whenever we give the input that we are going to give is the Vc max at 25 degrees Celsius. So if we give that input, we can obtain the VC max at whatever temperature of the leaf that we made the measurements in. Okay. Now the same thing is also used in the RUBP regeneration phase equation, where you know this term, this photosynthetic rate AJ is represented by this rate of electron transport into Ci minus tau star and all of that. In that J term is a function of the maximum electron transport rate, and maximum electron transport rate is a function of this temperature response function. So again, J max is the value of maximum electron transport at reference temperature 25 degrees Celsius. Now RD is also given by this Arrhenius equation, and RD is also a value. This RDT gives the value of dark respiration at any temperature. RD alone is the temperature, is the response function that we are giving. Sorry, it's the dark respiration that we are giving in at 25 degrees Celsius in this particular model. Now, if you want to use any other reference temperature, you have to find out again when this Kc value is going to be equal to 1. At what temperature is this Kc value going to be equal to 1? And then we can substitute in these equations. In this case, that is, I have taken these equations from soybean Biochro. These are the parameters used. And here the reference temperature taken is 25 degrees Celsius. Now another temperature response function that is used used is the John Eyring's Williams model. In this, similar to this Arrhenius, where you see there is T into the temperature into e to the power C minus HA by RT. We also have a term in the denominator that is considering the deactivation energy. So here activation enthalpy is there, and deactivation energy is also considered in this John Eyring's Williams model, and this is the equation that is given by this these scientists. So when it comes to photosynthesis, the TPU rate we represent in terms of this John Eyring's equation. This is again at a reference temperature VTPU into the temperature, whatever is the temperature, the enthalpy in activation enthalpy is 62.9, deactivation enthalpy is 182.14, C value is 25.5, S by R is given over here. So S is entropy term. So S is given 0.58 by the ideal constant is, sorry, the entropy divided by the ideal constant is written directly as 0.58 over here. Again, this is an equation that I've taken from the soybean model. It varies with plant, it varies with temperature, and it is to represent this variation of these parameters with temperature that we are using this temperature response curves. Then the third temperature response curve is the polynomial temperature response function. Again, this is like a polynomial equation, and the parameters like this the light response curve. We have the J term, we have the theta psi, and we have the phi psi. So theta psi is the convexity factor, is represented is represented as a function of temperature using this polynomial equation. And phi psi, that is the maximum quantum yield, is also represented as a function of temperature using this polynomial equation. And how are we going to obtain all these parameters? It is again through the method of curve fitting. Again, in the last class, I think, yeah, the previous class I had I had explained how we optimize, do optimization of the parameters. So by optimizing these parameters with the measured data, that is fitting these curves with the measured data, fitting the curves generated by all of these equations with the data that we have measured, we will be able to get the parameters, that is all these constant. What is 0.018 is for soya bean for a particular temperature. So we will get all these values if we are able to fit curves of temperature response and curves generated by these equations. So these are the temperature response curves which we require to fit. Then again, apart from the C3 photosynthesis, I had covered just basic concepts of C4 and CAM photosynthesis. So in C4 photosynthesis, the structure itself is a different. Grants and anatomy we call that the C4 plant. So you see that the bundle sheath, although there is bundle sheath around the xylem flowing cells, the bundle sheath is very more prominent in the C4 plants, and you can see the palisade cells are forming a cross section in this form. So why is this happening is because in the C4 cycle, the Calvin cycle is occurring in the bundle sheath cell, and in order for this Calvin cycle to undergo the bundle sheath, I mean, um, happen in the bundle sheath cell, the carbon dioxide that is available in this palisade cells is converted into oxalo acetate by this pep oxaloacetate enzyme, so PP enzyme, and it is PEP plus CO2 is going to form the oxaloacetate. Like RUBP is combining with carbon dioxide in the same way. PEP will combine with carbon dioxide to form oxaloacetate, which gets converted into malate, which diffuses into bundle sheath cell, releases a carbon dioxide molecule, which takes part in the Calvin cycle, and malate gets converted to pyruvate, which goes back into the palisade cell, and the cycle happens over here. So this is why photorespiration is not occurring in C4 plants, but here photorespiration occurs because the Rubisco enzyme has got high affinity for carbon dioxide as well as for oxygen. But in C4 plants, because of this mechanism, photorespiration does not occur. Now in CAM photosynthesis, the same thing that is happening in C4 photosynthesis is occurring in two phases. That is during night time, the carbon fixation of the Calvin cycle occur, and at night time the stomata will open. So in the night time, it will mean in order to minimize the water loss, the plants will open the stomata only during night time, and during this time carbon dioxide will get entered and it will be stored as malate, as malate. Oxaloacetate is converted to malate and it is stored in the cell. Then during the daytime when light is available, all the light reaction will occur and it will provide all the energy for the Calvin cycle to occur, and the inside the bundle sheath, then remaining processes of the photosynthesis will occur during the daytime. So this is the difference between C4 and CAM photosynthesis. CAM plants are again, since it's opening at night and daytime, this nighttime it is opening. So these plants are specialized to store water, like cacti and the what do you say, succulent plants. And pineapple is a CAM. So this is a comparison of C3, C4 photosynthesis. So before I end the class, I have a small test for you. I will be sharing it. You can attend the test, and yeah, after that I'll. So these are just one word questions. You can just attend. It is a test for the whole. I'm covering all of the portions. So that will be the end of this class. I wish you all the best. You can give the test, which will give me an idea about how much of what I've taught is been translated or has been communicated to you. Um, yeah, so please do attend the test. Okay, thank you, Anamta. Thank you for attending today's sessions, and I think you've been a regular. So all the best. So yes, do well. Thank you. You can leave the session. Thank you, Ryan. Wish you the same. Thank you, Harita. You can also leave the session. See you later. I think my end, that's okay. If you can't complete the test, I'll be posting the solutions in this. I think it's time for me to wind up. So thank you to you also for attending all the sessions and being a regular in the classes.
सॉरी मैम, मैं कंप्लीट नहीं कर पाया क्योंकि थोड़ा टाइम कम पड़
Yeah,
रहा
no,
था।
no, no issues. This is not like it
वो
is being
रिकैप
credit or
करने में कि क्लास में क्या क्या हमने पढ़ा और कैसे आंसर करें इसको हर क्वेश्चन का।
okay, no problem. So yeah, thanks for attending today's session, and I think you've been a regular, so thank you for that too. So all the best. Do well.
थैंक यू
Bye bye.
मैम,
Okay. Bye
थैंक
bye.
यू मैम, थैंक यू।